Hello, welcome to lesson 5.5. This is on the applications of higher order polynomials. We're really just going to work one simple volume problem. It's kind of a thing to just explore from class. We're not doing a whole lot of applications with polynomials here. I think once your understanding of knowledge and knowledge, once you've really deepened your understanding of polynomials through your math experience, and you learn certain techniques from calculus, then you'll really be able to apply these things. But for now, this is about what we can do. And the reason I say that is, we've talked about finding like what's a local max or a local min, right? So like this function I've sort of drawn here, it doesn't have an absolute or global maximum or minimum, but it does have local maxes and local mins, right? At the dots I graphed there. Thing is, you kind of need calculus to find those. It'd be like hard to find those algebraically. We don't really do that usually because calculus just makes it so much easier to do. So we won't be finding things like that. But we can set up functions, analyze them, and make sense of what they represent, okay? So in class, I basically just gave 25 minutes to do this problem. So honestly, if you're going to work in the spirit of the class, give yourself 25 minutes. Go through A through F, yeah? But once you've done that, once you've given it a good try, here's the sort of solution to this, okay? And I'll read the problem real quick. It says we're going to take a piece of cardboard, which is 10 by 15 inches. We're going to make a box out of it with an open top. And the way we're going to do that is by cutting equal-sized squares from each corner and then folding up the sides. So there's going to be, I'm going to just draw a picture because I really should probably switch these things around. So part B says draw a picture. So here's what you're doing. You're taking a box. Let's make a rectangle. Something like that, right? Come on now. Play nice. You're taking this, right? And you are cutting out a square corner. I'm going to try and make this as square as possible so that the side lengths are all the same. You're cutting out a square corner like this. And so you kind of have, if I make these dashed lines, right? These dashed lines are where you're going to fold, right? So I'm going to kind of boop, 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 boop. We're gonna cut this out. So cut out, right? These four corners. I'm just making the box. I'm just having a good little time sort of coloring these in. There you go, right? And so I'm going to fold up these flaps, and they're going to make the box. And so it'll look something like this. It's just going to make a basic rectangular prism. I can draw a rectangular box okay. But it's an open box, right? So it's kind of like open like that, right? That's not half bad. I'm kind of proud of myself. That doesn't look half bad. Made from this. So anyway, that's my picture. That's kind of what's going on. Now, here's the problems in question. So it says, let x represent the length of each square, right? So that amount you cut is x. This function that's given to you right here models the volume. I don't know why it says the different volumes. Maybe that's a typo on my part, sorry. It says a function this models the volume with respect to, I guess not. Different volume, that's whatever. This is the volume function, okay? Don't get caught up on the wording like I am right now. And so here's what part A says. It says write a function that models the volume of the box in factored form using the equation given. So I'm just going to take 4x cubed minus 50x squared plus 150x. And we're going to factor that guy. Always look for GCF first. I notice that 2x is a common factor. And I get 4x squared minus 25x plus 75. Now we'll do a little, a little thingy here. 4 times 70, 4, Mr. Spake. 2, silly. 2x squared, what are you doing? So 2 times 75 is 150, and then there's negative 25. So what, 15 and 10? You make them both negative. They multiply to get 150 and add to get negative 25. And then I'll just do my factor by grouping for quadratic trinomials, where I split the negative 25 into negative 10x and negative 15x, like so. And then I do GCF with grouping. So I factor out, let's make this a bracket. Yeah, you know what? Since these are official notes, I'm going to make that a nice bracket. Let's do 2x times x minus 5. We're going to take out 15 goes into 75 5 times, if you didn't know. 15, and then this is x minus 5, which leads me to show, I said show. So this is 2x times, it'll be 2x minus 15 times x minus 5. And so this represents the volume of the box in factored form. But that's it. It's just the polynomial completely factored, okay? I mean, come on, that's a factoring, but that's it. That's all it was. Now, part B is kind of making the realistic sense of what the heck is going on. So I've drawn my box, right? We set that out. We have the rectangular piece of paper, and we're cutting out those corners, folding them up, and making this box that's right here. Now, we'll ask ourselves, what are the dimensions of this box? Well, you see, this length, if you recall, the length of the box was 10 by 15. So, I'm sorry, I want to make that straight. Can you make that straight, please? Oh my gosh. Make that straight. That's better, thank you. So we'll call that 15. We'll call that 10, right? And that's those lengths. This length then, well, hold on. What's the length I'm cutting out, right? Well, the length you're cutting out is called x. And so all of those little pieces, right, this is also x. So you're cutting out x from both sides, like so. We've done a problem like this in the past. So the side length that was 10, you're taking x away on both sides of it, means it's 10 minus 2x. You're taking away 2 x's. The side length that was 15, you're taking away 2 x's also. And so you can see that this sort of inner perimeter, right, this border, right, that's 10 minus 2x by 15 minus 2x. This is the base, sorry, that thing I'm highlighting and outlining with my laser pointer, that's the base of this box, right? So the length by width are 10 minus 2x and 15 minus 2x. You might ask yourself, well, what's the height, right? What's the height of this box? Well, that this piece you cut was x. And so when you take this piece and you fold it up, it's x long, which means this length is also, this height is x. And that's your picture. I mean, that's pretty much it. I'm going to move the picture over here. I'm going to move this over here. Like that. Okay? It's got your nice pretty box. What a nice diagram. Just what a great problem. Put the T back there. Okay. Now, part C. It says, using your result from part B, what is the volume of the box, right? So, well, if I look, volume is length times width times height. So, V of x, based off the picture of the box, is the sort of it's the product of those three lengths, right? Length times width times height. So I'm going to do, we'll start with x first, 10 minus 2x, and then 15 minus 2x. And that's it. Let's say that's all, right? Done. And so now what part D is asking is show that your answers from part A and part B are algebraically equivalent, which means this thing you found for part A is the same as this thing you found in part C. So, what do I do here? What do I do? Well, let's take the result from part C. So from C, I'm going to do this in blue. Blue. From C. I see that v of x equals x times 10 minus 2x, and then 15 minus 2x. I'm getting sleepy. I'm tired. Mr. Spake is sleepy tonight. That's your volume function that we found based off length times width times height geometrically, right? Again, we want to show that that volume function is the same as this in factored form. So perhaps we could ask ourselves, see, I'm yawning. Oh, I told you I was sleepy. So can you factor this further? Right? I mean, you have it in a sort of factored form, but two things to keep in mind. One, GCF. Is there a greatest common factor you can take out? Two, is the lead coefficient of each factor positive, right? So that's two things to consider because we like it to be, right? We would prefer, if it's 5 minus x, we'd like to write that as negative x minus 5. Now, look, we don't have to. It's just that it's very standard to do that. It's just kind of the thing to do. Some people, I mean, there's instances where I leave it as 5 minus x. That sometimes is preferable. I'm just letting you know that it's very standard to just write it like that, okay? When you're doing functions, polynomials, things like that. So when you look at 10 minus 2x right here, two things. 10, 2. Both have a GCF of 2. Also, x is negative, so you can factor out a negative. So I'm going to factor out negative 2. And then I have my x here. Negative 2 taken away from 10, and I don't mean subtraction, I mean division, is negative 5. Negative 2 divided by negative 2 is positive 1, so it's positive x. And this is 15 minus 2x. But then notice 15 minus 2x. There's not a GCF between 15 and 2, but you could make the leading term positive by factoring out another negative. Like that. So I have a double negative on the outside, and that's negative 5 plus x. And I'm taking the negative out from this thing. So positive 15 becomes negative 15, and negative 2x becomes positive 2x. So it's negative 15 plus 2x. But notice a double negative, that double negative here at the front, negative times negative is positive. And then negative 5 plus x could be written as x minus 5. It doesn't have to be, but it could. And negative 15 plus 2x could be written as 2x minus 15. And you'll notice this is the result from part A, right? In part A, you found this. You found 2x times x minus 5 to 2x minus 15, like that, right there. So they are the same thing. Okay, part E says, what are the x-intercepts of this function? Well, if v of x in factored form is 2x, x minus 15, and 2x minus 15, x-intercepts are roots. So what makes these factors 0? 2x equal to 0, x minus 5 equal to 0, and 2x minus 15 equal to 0, right? So then x is 0, x is 5 by adding 5 to both sides, and then you add 15. So 2x is 15 means x is 15 halves. So your roots are those three numbers, right? It's 0, 5, and 15 halves. Or if you like, 7.5, like so. So those are your roots. You could write it, the x-intercepts are 0, 0, 5, 0, and 7.5, 0. So maybe another thing to write. Okay? All right, the last piece, this is it for the video. It says, which represents a reasonable domain for the volume of the box that v of x models? So a lot of students say, the heck does that mean? What is reasonable domain, right? So domain is your set of x values. So you input to the function, it's what you're allowed to put in, right? Now the thing is, this is a cubic function, and x cubed has all real numbers as its domain, always. Any cubic function's domain is all real numbers. But is it reasonable? Does all real numbers make sense within the context of the problem? Well, no. And what you want to do is go back to your box. You see this box here, right? In fact, we're going to take the box. We're going to copy it. We're going to make a copy right down here. No, not on which. No, not on represents. Here's over here. And we're going to move it down there, right? So when you say what represents a reasonable domain, I'm going to move you over. Don't forget that. No, I'm taking my time. I'm sleepy. I'm tired. I'm lethargic. Well, what can x be? What can x be? And you keep in mind something, and maybe perhaps I'll put this in yellow. Side length can't be negative, right? Side length cannot be negative or 0. Oh my, I can't spell. Oh, you can just see. You can just say, here's Mr. Spake. Well, that's not my hair. My hair is more like that, with my glasses and my smile and my belly. I say, there's Mr. Spake. I say, here I am, right? And you can say, he's falling asleep. He's yawning. You're saying, me. Okay. Sorry, the sleepy sillies are getting to me. The side length cannot be negative or 0. Is that right? So what you want to do is set each length greater than, not equal to, greater than 0. So just take each length. X must be greater than 0, right? 10 minus 2x must be greater than 0, and 15 minus 2x must be greater than 0. Now, these are very simple Algebra 1 linear inequalities, two-step equations, right? Or two-step inequalities, I should say. Add the 2x over, right? 10 minus 2x is greater than 0. Add the 2x to both sides. 10 is greater than 2x, divide by 2. 5 is greater than x. Or equivalently, x is less than 5, right? So conclusion, x is less than 5. And the other one should lead you to x is less than 7.5. Now, condition, right? Must satisfy all, right? Must satisfy all three. I don't want to put up, okay? Must satisfy all three. So x has to be greater than 0, and it has to be less than 5, and it has to be less than 7.5. Thing is, if it's less than 7.5, suppose it's 6, right? Suppose x equals 6. Then 15 minus 2x, that's 15 minus 12 equals 3. That's good. But 10 minus 2x is 10 minus 12 is negative 2. That's bad, right? In fact, we're going to put an angry face. We're going to say, here's my face. I am angry, right? So don't do 6 because that makes this, right? You can see that it's an and statement. All 3 must be true in order to keep this side length positive, right? If I pick anything equal to that or whatever, that's not good. So strictly less than 5. We're not really going to use the less than 7.5 because it must be less than 5 to satisfy this. And so anything between 5 and 7.5, that's not going to work. Okay? So, answer, right? Therefore, my little 3 dots, I love my little 3 dots, x is in between 0 and 5. And that's not a rectangle. I'm going to draw my rectangle like this. And there it is. Nope, trapezoid still. I know, if you watch all my videos, you'll notice how much I struggle to make these rectangles. Okay, and that is it. That is the reasonable domain for x. You just basically set all the side lengths greater than or equal to 0. Sorry, not equal to, just strictly greater than 0. And then just know that, hey, it must satisfy all 3. Because if it doesn't satisfy all 3, it makes one of the side lengths negative, right? You know that x has to be positive because of this side length. And this side length is longer, so you're allowed to take away more, but it's going to be limited by the shortest side, right? 10 minus 2x, shortest side, means you can only cut away so much. And remember, it makes sense, because if you have 10 minus 2x, if your side length is 10 and you try to take away 6 from both sides, well, 6 and 6, right? That's a side length. You don't have 6 to take away from on both sides. You only have 10. The most you could try to take away is 5, right? And so it's limited that way. For fun, let's look at the graph. Look at graph. So if I sketch the graph based off the intercepts, right? So here's 0, 0, here's 5, 0, here's 7.50. That's probably a little bit closer like that, okay? So that's 0, that's 5, that's 7.5. Your graph is odd, right? The degree is odd, and the lead coefficient is positive, which means, right? And you say, what do you mean? How did you know that? Look over here. Look at your volume function. The degree was 3. It's a cubic function, so the degree is odd, and the lead coefficient is positive. Is 4, which means the end behavior, the right points up and the left points down, and it does some wibbly wobbly in the middle, right? So, oops, I come over here and I say, oh, look, it goes up from this, curls down, goes back through here, and then continues down like that. And so the graph roughly looks like this. And this represents, right, the graph represents volume must be positive. And the only region where it's positive, do I have like a light green like this? The only region where the graph is positive is in between 0 and 5, right? X is 0, less than that. This is where it's positive. Now, granted, it is positive over here as well. So it does go on to infinity that direction, but, right, if x is greater than 7.5, then the side lengths are negative, right? These sides are negative. And there you go. Man, that's a lot of stuff to that's a lot to just fit in that little space there. But yeah, hopefully that gives you some sort of guidance. How about I lasso that and move it? Anyway, you don't need to stick. I'll just do that after the video. Anyway, that's it. Those are the notes. It's one application problem and we're done. It was just something we were exploring and talking about. On this other side, I'll just give a quick explanation for this. I offered this as extra credit for my class as +5 quiz points. Depends on if you have a different teacher, though. I don't know if they've offered it. Up to you could ask. You say, hey, is this for extra credit? Mr. Spake's offering it, right? You could say that. But it's their discretion. It's whatever they want, right? And what this is a short extension on sort of using calculus to figure it out. You say, calculus, Mr. Spake, I can't. Yes, you can. You can do it, all right? Because I did all the calculus for you, yeah? Basically, it says there's a special function we call v prime of x, v prime of x. That's what that little apostrophe says, prime, right? So v prime of x is a special function. I'm not going to spoil the fun right now. I don't want to tell you. You can learn in calculus when you take it, right? But v prime x is a special thing that comes from v of x. And it's used to find minimums and maximums. So we have these 2 points, right? A local min and a local max. And in calculus, you'll be able to use this special function to find those points. So for fun, if you want to just do this on your own, run through all that, right? I'm not going to talk about it in this video. I'm not spoiling it. It's for you to investigate. But it's a way you can find local maxes and mins without graphing, which is kind of cool. Because if you look at our graph, well, we don't have any idea where these local max and mins are, right? We have no clue. So, okay. That's the video. Hope you enjoyed. Hope it was helpful. And sorry for being so sleepy. But thanks for bearing with me here. Have a good day, night, or morning, or whenever you're watching this, and take care.